Welcome to the Claude Hocott Lectureship in Petroleum Engineering. My name is John Olson, and I'm the Department Chair of the Hildebrand Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. And it's my pleasure to introduce to you today our graduate seminar speaker, Dr. Eric Van Oort, who is also a faculty member in the Hildebrand Department. Dr. Van Oort became a professor in petroleum engineering at UT Austin in 2012 after a 20-year industry career with Shell Oil. He holds a PhD in chemical physics from the University of Amsterdam. He's co-authored more than 200 technical papers, holds 14 patents, and is a distinguished member of the Society of Petroleum Engineers. He received the 2017 International SPE Drilling Engineering Award and was an SPE Distinguished Lecturer. At UT Austin, he directs drilling-related R&D in two major research consortium called RAPID and CODA, with over 25 industry company sponsors covering drilling automation and control, sensor design, big data analytics, complex well construction challenges, and well abandonment and decommissioning. Recently, he has become involved in geothermal drilling through UT's new Geothermal Entrepreneurship Organization called GEO, for which he is the technical lead of that initiative. Without further ado, let me give you Dr. Eric Van Oort.
I can make it worth your while for the next hour or so. John, thanks for the introduction. Yeah, so I've spent most of my career, for those of you that don't know me, with Shell, which was a fantastic experience. Shell gave me lots of opportunity to experience different environments, working in deep water and also in low-cost land operations and everywhere around the world. And I became a professor in 2012, actually started lecturing in 2011 at UT. So this year marks my 10-year anniversary lecturing at UT. And I get myself involved in a lot of different stuff, which is a lot of fun. The biggest things that I work on these days have to deal with the big challenge of well decommissioning and abandonment. That actually has an interface with geothermal, which I'll touch upon at the end of the lecture. My biggest consortium is called RAPID, which stands for Rig Automation and Performance Improvement in Drilling. And then I work with the Geothermal Entrepreneurship Organization, and many of you may know Jamie Baird, who has been leading this in quite a visionary way. The work that I'm going to talk about in this lecture has to do with RAPID. And in RAPID, we work on sensors and automation control systems, on modeling and simulation, on intelligent mechanization and robotics, and then big data analytics. And again, you'll see those themes kind of coming back in this discussion on how we're going to drill these deep closed-loop geothermal wells. So on RAPID, it has had very good operator support over the past years. We're actually losing some members, and it's kind of funny to see that we're losing some of the larger companies, whereas the smaller ones are continuing on. But I'm happy to report that recently we signed up the first geothermal company, which is Ever, which is currently based out of Canada, and we're starting to work with them on their closed loop geothermal wells. And the picture that you see there is the Everlight concept that Ever actually has drilled already in Canada. So this is the presentation. I'm going to give you a little bit of an introduction to what deep closed loop geothermal wells are and how they're different from EGS wells. I'll tell you a little bit about the advanced modeling that we've done in my group on the power production of such wells. And then we're going to talk a little bit about the technical feasibility of these wells, right? What we can do right now and where some gaps and needs are. And we'll talk about deep hole making, wellbore geomechanics, high temperature materials and sensors, some economic analysis, and a pretty exciting topic, which is geothermal, artificial intelligence, and machine learning. I'll talk a little bit about some additional oil and gas opportunities and why it makes sense for oil and gas to be particularly interested in becoming involved in geothermal. We'll talk a little bit about the way forward, how we make some of these concepts a reality, and then we'll have a conclusion and some questions. Most of you know this. right? The core of the Earth has about the same temperature as the surface of the sun. It's about 6,000 Kelvin. And the Earth's heat content is phenomenal. It's a ridiculous amount of heat energy. It's 12.6 times 10 to the 30th joule. And every second, the Earth kind of flows about 50 times 10 to the 12th joule from the core to the surface, about 50 terawatts that are being radiated out in space. And comparing that to kind of the global power consumption by humans, that's about 15 terawatt. This actually has created some confusion among skeptics of geothermal, saying, well, that means that we'll have to cover 30% of the Earth's surface with geothermal wells if we want to generate 15 terawatts. That's not the case. If you go deep into the Earth, you have access to much higher temperatures, and you can extract a lot of energy from this. Just to give you a sense for how phenomenally large that heat reservoir in the core of the Earth is, if you were to extract that 50 terawatts continuously for 1 million years, right, about 3 times our current consumption, then after 1 million years, you will have depleted that heat reservoir by about 0.01%. And of course, at the same time, there is radioactive decay happening, and you can consider this a fully kind of renewable resource, right? There's nothing that we can really do to really deplete that resource. And that's the phenomenal opportunity that we have ahead of us. Most people, when they think about geothermal, they are familiar with enhanced or engineered geothermal systems, or EGS. You see this on the left. That system basically uses injection wells where we're pumping cold fluid, circulating fluid down, typically water, and we're using either a natural or an induced fracture network, and then are producing water and steam to surface through one or more production wells. And then we use that to drive steam turbines to generate electricity. So that is EGS. Closed loop is basically a system that has a conduit where the circulating fluid never leaves the conduit. It's basically a simple heat exchanger where you have some kind of a loop, like the U-loop that you see over there that Evo is pursuing, in a warm reservoir, and you circulate fluid around, and that fluid gets heated up through its exposure in the wellbore. So that is the difference between EGS and closed loop. Although right now, I think in the terminology, closed loop is still kind of seen as a subset of EGS, but I'll make that distinction between EGS and closed loop here in this presentation. Okay, why do I like closed loop? A lot of what I'm going to tell you about drilling practices applies to EGS and closed loop in a very similar way. I focus on closed loop for this reason. This is kind of comparing the risk profile of EGS and closed loop geothermal systems. And the problem with EGS, and don't get me wrong, I don't want to discourage anybody from working on EGS systems. But what has happened is that induced seismicity has been reported at several sites, big events in Basel and in Pohang in South Korea, and more recently in Fonroche in the Alsace in France. With closed loop, we don't expect induced seismicity because we're not pumping fluid through a fracture system, and we don't expect to induce any slip on faults. There are other concerns with EGS as well, which are surface gas emissions. You're pumping fluid through an open system, and it can pick up gases such as H2S, and you might vent that to surface. That is not a concern in closed loop systems. Your permeability may plug in fracture systems. That is not applicable for closed loop. And then the prediction of energy production over time, because the changes that can happen to the fracture network make it a relatively high uncertainty. And with closed loop, we have more reliable calculations. So this is why I favor closed loop systems. And I am a bit concerned that if we, for instance, build a deep EGS well in the US and you get a high profile kind of seismic event, you could taint all of geothermal by association. And I really don't want that to happen. Until recently, if you talk to people in the geothermal industry about closed loop, then they would tell you, oh, we've looked into this and it doesn't work. No, it's not going to work. And the reason for that is that historic work on closed loop has considered kind of shallow, small scale well designs. And you see some of this here. This is actually quite recent. Some graphs from a paper by Oldenburg with Greenfire in 2016. Very good work, very good modeling work, but considering wells that, as you can see here on the right, let me change to a pointer. The wells that will only go down for about 2.5 kilometers, and then we have an 1,100 meter horizontal. And this well, in this relatively low temperature environment where the fluid temperature that's coming out is about 75 degrees centigrade, will generate a few megawatts of power. And that is, of course, insufficient to get really excited about. If you compare that, for instance, with deep EGS, that can generate tens of megawatts, right? So that's why people, until now, have not been really excited about closed loop. If we really want to boost the power of closed loop, we need to go deeper. And that's what I'll be talking to you about right now. So most of you are probably familiar with these beautiful, fantastic maps generated by SMU that show the US geothermal gradient behavior with depth. So this is the map at 10 kilometers. And you can see that at 10 kilometers for most of the US, kind of following on this kind of darker yellow color, we have temperatures above 200 degrees centigrade. And I'm particularly interested in well conditions where the in situ temperature is above 200 degrees centigrade. And you see that particularly in the west side of the country, we have areas there, especially west of the Rocky Mountains, right, with very high geothermal gradients. But even here in Texas, on the west side and south side, we have this, even here in the Appalachians and so on. There are some elevated gradients there as well. What does it look like for the rest of the world? Well, here is Europe and Australia with some information. For instance, from NREL. This is only at 5 kilometers depth. But you see there are areas of elevated temperatures here in Germany and my own fatherland of the Netherlands, here in the Alsace, of course, in central France. You've probably heard about earthquakes in Turkey. Well, it's seismically active and you have very high geothermal gradients there as well. This is Australia. Unfortunately for the Australians, most of the more interesting geothermal areas are in the sparsely populated north and the central part of the continent. Here is Africa, and Africa is particularly interesting because what I want to talk to you about is basically a concept where we can do geothermal wells anywhere, so anywhere around the world. And if you can do it in Africa, then you can make a real difference there. There's not a lot of information available there. There's an excellent publication by someone called Duncan McGregor, who has kind of shown some gradients, primarily, of course, with oil and gas development offshore Africa, and then in places like Algeria and Libya. Here are some of the gradients that have been mapped for South Africa, and there appear good opportunities there as well. This is for Texas. So if you're really interested in Texas, and if you're really interested in doing something on university land, like a pilot, then we actually have some areas with some elevated gradients that overlap with university lands, and I'd love to work on a deep closed-loop geothermal pilot there with of course the students from our department on these university lands. That would make for an interesting project. Okay, what are we talking about? Well, here are some schematics, and do take me on this that these are schematics. These are not the actual well trajectories that we will drill. I can already hear my critics kind of laughing, going, Van Oort is going to go 7 kilometers down into the earth and then make a right turn. No, this is a schematic, right? When you drill an actual well trajectory, you have to take into account kind of weight transfer, torque and drag, and so on. But just to give you an indication, I've already shown you kind of these U-shaped wells where you have an injection well bore and then some kind of a heat exchanger. The trajectory really doesn't matter all that much as long as you get enough exposure to the hot formation, and then you return it back to the surface. This is an open loop. You could also think about a closed-in loop, or what is called pipe-in-pipe. In a well like this, you pump fluid down the backside, so you pump it down the annulus, and you let it heat up, and then you pump it, for instance, using vacuum-insulated production tubing on the inside back to surface. Now, if you really want to start generating more power, then you need to go to a larger depth. So typical geothermal wells don't go beyond 5 kilometers of depth, and we have to start thinking, if we want to do this all around the world, right, at depths that are 7 to 10 kilometers, and then you have pretty much anywhere kind of temperatures in this range of 200 to 350 degrees centigrade. You also have to think about, of course, getting this exposure to the hot formation, right? And as I said, the exact shape doesn't really matter as long as you get enough whole length exposure to the hot reservoir. And these are just two examples, right? And I've shown here kind of different configurations for these deep loops. Okay, a way of drilling this, if you were wondering about going 7 kilometers down and then 7 kilometers in terms of a lateral, right? You can drill this in two parts. You can drill 7 kilometers down and then a 3 kilometer lateral, and then do it from the other side as well, and have it link up and intersect the well bore. We do this with ranging technology, for instance, when we drill relief wells. The reason why we have to go to this depth, I've given some information here. The average surface temperature around the globe is around 15 degrees centigrade. Average geothermal gradient is about this 20 to 30 degrees per kilometer. Of course, traditional geothermal areas can be significantly higher than this. And you see that if I need temperatures higher than 200 degrees, then I'll typically have to go to this 7 to 10 kilometer range. That doesn't mean that we have to go there straight off the bat. You can go to existing geothermal areas or areas with higher gradients and drill kind of shallow hot loops. And I would definitely recommend that you do this first in a phased approach to prove up some of the technology and some of the modeling. An interesting thing is that you can go to existing geothermal areas that do not have fractures. In those areas, EGS will not work, but with closed loop, we don't need any fractures, right? So where these areas have been traditionally uneconomical for geothermal companies, but for closed loop, they're pretty much ideal. Okay. Let's talk a little bit about deep drilling. So there's actually quite a bit of experience, actually a very long experience with that. You may have heard about the Kola super deep hole in Russia, 12 kilometers vertically into the earth. It took a long time to drill that. It actually took years. But it was also done with 50-year-old drilling technology in the Soviet Union. Early on in my career, through Shell, I was actually involved with an experiment that the Germans did called the Kontinentale Tiefbohrung, or KTB, that went about 9 kilometers vertically. You may have heard about this GQ drill ship, kind of a research vessel that was meant to drill 7 kilometers below the seafloor, operated by the Japanese. And then, of course, in more recent years, in the last decade, in the tertiary play in the Gulf of Mexico, BP, Chevron, and others have started drilling these monster wells to these tertiary plays with, for instance, Tiber originally drilled by the ill-fated Deepwater Horizon, going to a depth of 35,000 feet. So that is more than 10 kilometers. So quite a bit of experience already with deep drilling. When it comes to drilling at an angle, so directional drilling, quite a bit of experience there as well. Here are some examples again from oil and gas, the extended reach wells that were drilled at Sakhalin by ExxonMobil. You see the big Parker rig that is sitting there on the beach at Chivo, drilling these world record wells that have already exceeded kind of 13 kilometers. They're shallow, but with high horizontal step out. And the Parker rig, of course, by Bobby Parker's company, who has been a great benefactor of the department. I think Bobby Parker was instrumental actually in getting me to UT. Some examples from oil and gas, high pressure, high temperature drilling. So in oil and gas, we recognize normal high pressure, high temperature, ultra high pressure, high temperature, and extreme high pressure, high temperature regimes. And this is some data from 2012, so already 10 years old, primarily data from Total, where you can see that oil and gas have drilled in this range of 200 to 350 degrees centigrade, right? And this is also the range where we want to be for these deep closed loop geothermal wells. And we want to preferably be at the low pressure end of this. That reduces the complexity. Good. If you want to start drilling, then you have to, of course, have motivation. You need to have a reason to do this. And I started to become really excited when I started to see modeling results from my excellent research group at UT. We developed multi-phase flow models for, of course, hydraulics in drilling, for control of managed pressure drilling. And we've extended that to the geothermal realm. And if you want to do this right, you have to do some fairly sophisticated modeling, kind of combining 4 coupled equations for mass conservation, momentum, energy, and density. And I'm not going to go into the details on this. If you want to know more about this, we're actually getting ready to release a paper at the upcoming SPE IDC drilling conference. It'll take place in early March, so actually less than a month from now, and we'll give you all the details of the modeling in that paper. But we started to look at modeling some of these closed loop wells, and again, here is this example of a well that is 7 kilometers down, has a 7-kilometer lateral, and a 7-kilometer return back to the surface. That's 21 kilometers, but you could drill that as 2 10-kilometer wells. The circulating fluid is water. The in situ formation temperature is 225 degrees centigrade, so on the low end. We're going for an open hole completion to maximize heat exchange. It's 8.5-inch hole size, and we're flowing at 1500 GPMs. And you can see how this behaves. Initially, we're assuming that we've left the well alone for a long time. Everything has equilibrated to in situ temperature. And then we initiate circulation. And then you see how kind of temperature of the returning fluid starts behaving. Initially, you start circulating very hot fluid back to surface. You need to control the phase behavior of that fluid very carefully. And then you start building up a steady state where you are circulating at a very high rate, about 150 degrees centigrade liquid back to surface. And again, you control the phase behavior. You don't let it flash to steam until you have got it back to surface and bring it into a steam turbine, for instance. You see also the behavior of the in situ temperature near the wellbore. You're actually cooling down the wellbore, but at some point you'll get a steady state that sets in, with heat, of course, being replenished from the far field. And this is all governed by the formation's heat capacity and heat conductivity behavior. If you then start looking at the graph here on the right, you can calculate what the net thermal power is that is coming out of this well. and it's on the order of about 50 to 60 megawatts. Now I need to be careful here. What we calculated, and I'm a well engineer, right? So I'm looking at the well only. I'm just looking at how much power can I get out of the well and how much power am I using, for instance, with the pumps to circulate the fluid around. So it's just the energy balance of the well itself. I'm not figuring in any losses, which might be significant from any surface equipment, for instance, losses that you get in your turbines to generate electricity. If you want to boost the power further, well, then you have to go to higher temperature environments, potentially more loops, as you already saw from the Ever example, a larger wellbore diameter, instead of 8.5 inch, go to 12.25 inch, larger flow rate then as well, and potentially a change in the circulation fluid with something that has a better heat capacity than water. So there are ways to further boost power to offset losses on surface. So let's talk a little bit about drilling, right? And I personally don't like the hype that is going around right now saying, oh, well, oil and gas is going to take over. They know how to do this, right? And we're going to show how geothermal should be done. The geothermal industry, if I were working in geothermal, I would be pretty offended by that. And geothermal has achieved a lot as well. I think oil and gas can add a significant amount to this in a very collaborative approach. So here are some of the recent achievements. And if you're interested in this more, I can highly recommend papers by Doug Blankenship, who is kind of the guru of geothermal drilling. He's written a very nice geothermal drilling manual, for instance, that you can find easily on Google Scholar. So geothermal drilling, has been accomplished above 450 degrees centigrade, with the going in Japan up to 500 degrees centigrade, and people in Iceland drilling into magma chambers. Well depths typically don't exceed 5 kilometers, but some wells have been as long as 10 kilometers, maybe not in true vertical depth, but in total length. Various bit types used. The workhorse are still kind of tungsten carbide insert bits. PDCs yield a superior rate of penetration, but you need to prevent them from getting damaged. And then there are there's compelling evidence that mud hammers may do very well. I'll come back to that in a moment. If you want to drill directionally, people have used kind of passive assemblies, kind of what we call pendulum, fulcrum, and packed assemblies that don't give you any azimuthal control and very little directional control, in fact. High temperature materials, quite a bit of work there as well, also sponsored by entities like DOE. We have cementing solutions up to 350 degrees centigrade, fluids at 315 degrees centigrade, and then you need to derate casing and connections for temperature, and you require corrosion resistance, particularly in EGS wells where they could be subject to, for instance, attack by H2S. The biggest issues in kind of conventional geothermal drilling have been low rate of penetration in drilling hard rocks, lost circulation, casing and cementing, and then of course directional drilling in these high temperature environments. How is this different from oil and gas? Well, in oil and gas, we know that wells deplete because of kind of finite reservoirs. In geothermal, we may have semi-infinite reservoirs. And if you put these wells together, they could live for a much longer time than, and they're not on a depletion curve like oil and gas wells. So that could affect the long-term economics, beneficially affect the long-term economics of geothermal wells significantly. The production hole sizes on geothermal wells are typically larger than in oil and gas. You drill, when you drill deep, you drill metamorphic and igneous rock. So you go out of sedimentary rock and go drill granite and basalt, which is of course at high strength and can be abrasive. You need to cement annuli back to surface. You can't leave yourself trapped annuli with fluid because that will expand when the well heats up and could cause casing collapse. The wells can be drilled in more benign poor pressure frac rate environments, and I'll come back to that in a moment. Severe losses are a problem on all deep geothermal wells, and if you go for an EGS concept, you need to be a bit careful in plugging those fractures up because you want to use them later on for your production. We don't have that problem actually in a closed loop because we can be very aggressive in dealing with losses because we don't rely on fractures to produce. There are cost comparisons made. I'll get into this myself in a moment. And then, of course, the number of geothermal wells that are drilled annually are dwarfed by the number of oil and gas wells that are drilled. And this has a bit of an influence on, for instance, how you use machine learning techniques to analyze data sets. So for the remainder of the presentation, I'm going to talk about 5 areas, basically being deep directional drilling, wellbore geomechanics, high temperature materials, a little bit on economics, and a little bit on artificial intelligence and machine learning. And the picture on the right is one that I took visiting Iceland, the Krafla facility there in Iceland. If you've never been to Iceland, that should be on your bucket list. That is the closest thing that you will ever get to visiting another planet, unless you want to die together with Mr. Elon Musk on the first missions to Mars. Some levity before we get into the serious stuff. I found this on the web and I found it kind of humorous. I don't know if this is actually official United States, but it says the reason why you can't dig a hole through the earth and come up the other side is because your shovel would melt. That's it. That's the only reason. Somebody remarked that says, what if you bring a second shovel that you put in a fridge beforehand and make it cold? And the answer then is yes, that'll work. Aptly are the simple so named, right? But now let's get to the serious stuff. So let's talk about deep hole making. So on deep hole making, as you may know, people are pursuing very advanced technologies, trying to break rock with spark bits and plasma bits and lasers and millimeter wave technology. And this is all very exciting, and it is rightly sponsored by entities like the Department of Energy and ARPA-E. However, I'm still a bit skeptical that these are going to deliver practical solutions in the foreseeable future, being in the next 10 years or so. And the reason why I tell you this is that I have this little booklet here. I hope you can see it. It's called Novel Drilling Techniques by a legendary drilling engineer called Bill Maurer. And he's still alive. He lives here in Austin. He's retired here. And he wrote this in the 1960s. And guess what he's talking about? He's talking about spark bits and plasma bits and lasers and millimeter and microwave techniques. So these have been around now for something like 60 years, right? So based on the fact that they've been around a long time and still haven't been implemented, I think it's going to take still a little bit of time before they mature. Again, I fully am behind these developments, but it may take a while before we see them in actual practice, drilling long sections of wellbores. Instead, we can do something to make conventional technologies work, right? If you can get PDCs to work in hard rock, you have hybrid bits now that marry the best parts of rock bits and PDC bits. Mud hammers can be used. And then there is abrasive jetting and particle impact drilling that has also matured. And maybe you can use some of these things together, right? What I also say is that these techniques actually work by failing the rock by heating it up and getting some kind of a thermal failure, which is kind of interesting if you're already in a high pressure, high temperature environment, right? Cooling might be more effective. Cooling of the rock might actually cause thermal fracturing. And so using cooling, for instance, with some of these technologies could be very interesting. Okay. So what do I think we should do in the short term until these more advanced technologies mature? Well, focus on making advanced bits, hybrids, and mud hammers work. Look at combinations of technologies, maybe PDC with abrasive jetting or mud hammers with cooling. I've written several papers, for instance, on thermal fracturing caused by cooling. A large potential benefit from drilling efficiency optimization. I'll get to that in a moment. This is the single biggest opportunity to get well costs down, and we can leverage learnings that we've had from shale wells. Novel high temperature directional drilling and MOD LWD systems. Companies like Baker and others have already developed these, right? Baker has high temperature motors that can handle 300 degrees centigrade. They haven't put them in production yet because there's no market for them currently. We can talk to rig manufacturers and talk about the rigs that we would need to drill these very sizable wells. And then we can leverage ERD and HPHT drilling expertise. Also, I think a big enabler for these wells is going to be MPD application. In fact, it's going to be crucial. And I'll talk a little bit about that at a later slide. One thing that we've learned in the recent past, let me see if I can get this to work. It did work. And now it, of course, doesn't work. Let me see if I can get back to here we go. Hope you can see this. One thing that we learned is that bits these days are really, really good. Bits can drill really, really hard stuff. What we found out is that bits mostly get damaged by drilling dysfunction, so by vibrations. And you see kind of the vibrations here on the left in axial, torsional, and lateral modes. And this is an older video by Schlumberger where they did a test in their lab where they're rotating a tool joint. And you see this tool joint not nicely rotating in the wellbore, but it's bouncing against the walls of the wellbore. And this is a phenomenon called whirl. And here you see this whirl going out of hand. This is what we call chaotic whirl. And when this happens, of course, you will rapidly damage drilling assemblies and bits. And we've really started to learn more about this when we started drilling shale wells. And we started to learn how to avoid this and optimize this and drill these shale wells a lot faster. So this is a real benefit that comes out of the shale revolution and horizontal drilling. This is what it looks like, right? Here you see a tungsten carbide insert bit on the left, and then 30 minutes of whirl in a hard sandstone basically leads to this. Let me go back to my pointer, where the cutting structure is completely eroded. Here you see a PDC drilling some harder rock with whirl and stick slip. And when we pull the bit, it's damaged beyond repair. And you see that the outer cutter structure has been completely demolished. It's completely missing. This is what we call a ring out of a bit. And if you can prevent this from happening, if you can diagnose this in real time and prevent it from happening, then you can drill faster and longer. And that's exactly what we need in geothermal wells. Okay, going on with the geomechanics. What has made deep drilling and high temperature drilling in oil and gas so difficult and so costly is that we drill into these sedimentary basins, these hydrocarbon systems, where oftentimes there is no drilling margin. And the drilling margin is the difference between the fracture gradient and the pore pressure. And you see that for a well here on the right. And when you get this deep with no margin, you will suffer from well control problems and borehole stability problems and lost circulation problems. And before you know it, your well is going over budget by hundreds of millions of dollars. If you don't believe me, go talk to ExxonMobil about their Blackbeard experience and Shell about their Joseph well. And in more recent history, Freeport McMoran on Davy Jones. The great thing about drilling deep geothermal wells is that we don't have to drill them in these narrow pore pressure fracture gradient environments. We can do it in a system where we have a much wider margin, and that'll significantly benefit drilling. I've already indicated that I favor an open hole completion if it can be done. You get optimum heat transfer there. we can really leverage what we've learned in oil and gas on geomechanics. So how we deal with lost circulation, with wellbore stability, understand the effects of cooling and heating on the wellbore stress state. And then I think what we have to offer also to geothermal is managed pressure drilling technologies. I've been foolish enough to take on the assignment of writing a book on managed pressure drilling. It's a phenomenal undertaking, but it's a fantastic subject. And technologies such as continuous circulation, applied surface back pressure, and mud cap drilling can all be used to drill deep geothermal wells faster, quicker, with more control. On high temperature materials and systems, quite a bit of progress has been made. All of this, by the way, that I'm showing you here is in that SPE paper that I mentioned, and I'll come back to that in a moment. So ongoing developments to get to high temperature tools. Regular tools are about stable to about 175 degrees centigrade, but there are new developments, new materials such as silicon on insulator and silicon carbide transistors that can go at 300 degrees centigrade and even 450 degrees centigrade and beyond. I've already mentioned mud and cement. You want to get away from Portland cement if you go to higher temperatures and go to alternatives. My group at UT is working on this very heavily. We work on systems called geopolymers, which have phenomenal casing to cement bond strength. You see an example here on the right. Portland cement, OPC, this is ordinary Portland cement, usually only has a very low bond strength to casing. That is a problem for zonal isolation. It's the reason why many shale wells after hydraulic fracturing develop well integrity problems. For instance, these new materials, these geopolymers that can be stable up to 800 degrees centigrade, show phenomenal bond strength. And you see a typical result, recent result out of my laboratory. So plenty of interesting developments there. Let me talk a little bit about economics. This is usually where people start off when they talk to me about geothermal wells, particularly companies and investors. This is what they want to know first. First of all, you have to understand that the economics of these wells is really determined by the depth and temperature, the reservoir contact length and time, and flow rate. Those are really the three big things that determine the economics. Now, we have to extrapolate here because the wells I'm talking about have not yet been drilled to the same scale. There's a very nice cost model by Lukowski of 2014 that actually uses money of the day 2009 for oil and gas and geothermal. But again, there we're extrapolating. But here you can see what the costs are. This is based on historical geothermal well cost. And you see that, for instance, a 10-kilometer well, based on historical cost, would cost about $40 million. So if you would have to do two to get to my U-loop, you'd spend $80 million for something that can deliver about 50 megawatts of power. The targets typically that people are looking for to achieve are a capex of less than $2,000 per kilowatt. For the entire project, by the way, not just the well, but the well cost will be 60 to 70% of the overall cost. And then a levelized cost of energy that is on the order of something like $20 to $30 per megawatt hour, so 2 to 3 cents per kilowatt hour. There is a significant range of error and uncertainty around this right now. Only when we start drilling some wells and do that in a phased approach, drilling shallower wells first, right, will we be able to firm up those cost estimates. The last technical thing that I'm going to talk to you about is this, which is also the thing that I'm most excited about. If you want to get well costs down, then this is the way to do it. It's artificial intelligence and machine learning. The GeoVision report by DOE already indicates that we might have some problems right now in geothermal, saying that the oil and gas and mining industries drill tens of thousands of wells per year in kind of well-defined environments, collecting and analyzing large data sets of drilling data has allowed these industries to optimize drilling approaches for specific conditions and subsurface environments, and that is true. The data sets for geothermal are much smaller. And whereas in shale, we have been able to get away with kind of a trial and error learning curve and learning very fast from our own learnings, but also from what the competition has learned, right, and capitalizing on that. We need to have a different approach with geothermal going forward. So you need to put some effort into a more focused approach. And I could spend just a lecture, and in fact the whole course on this. I'm going to show you some examples of things that I'm really excited about, something that my group at UT, my rapid group at UT has done. We've been working for quite some time in the oil and gas domain right now on data analytics, AI and machine learning. We've, for instance, worked with unconventional operators to extract data and information and thereby value from big data sets. You can use, for instance, spider bots to mine through your data and pull out the bits and pieces, the nuggets that tell you, for instance, on how to optimize your drilling performance, and have been remarkably successful with this. You can take these approaches also to real time and look at real-time drilling limiters, for instance, like the real-time behavior of vibrations. Everybody has these days heard about the use of the mechanical specific energy, which is kind of funny because that's been around since the 1960s. Although Fred Dupriest with ExxonMobil has done a great deal to popularize that in recent years. There are other indicators that can be used here, other indicators such as bit aggressiveness and stick slip alerts and several others. You can actually use these in real time to optimize and actually alert you and actually inform automation control systems, because we will need automation control if we're going to be very susceptible to bit damage. For instance, we need very smart systems that can identify drilling dysfunction quickly and take corrective actions. And you don't want to leave this to humans. You want automated control systems to do this for you. So my group works on, for instance, smart auto drillers that can be used in a fully automated closed loop drilling mode. Closed loop now in terms of the closed loop for control. To optimize your drilling performance. And that'll be the future both for oil and gas as well as geothermal. Mark my words. Okay. What are some additional oil and gas opportunities? Well, a big opportunity, but we need to be a bit skeptical about this, but it's the repurposing of old wells for hydrothermal and geothermal well purposes. As I said, we need to be a bit cautious. There are some literature studies that are very optimistic about it, but we need to look at the practice of this. Geothermal wells require excellent well integrity. They really need to be set up for thermal loads. You also need fairly large hole sizes. That may not be possible with your existing well inventory, but I don't want to discourage anybody, because plug-in abandonment is one of the biggest challenges in oil and gas. It's zero return on investment. The asset retirement obligation of many operators runs into the billions of dollars, and this may be a way to partially offset some of that. We also have a very skilled and trained workforce that can be redeployed. Very relevant expertise. I hope to have convinced you of that in this presentation. And then, of course, we can work with oil and gas companies to make good on their promises that in their green energy transition. I see John showing himself on the camera, so I'll finish up, John. I know. So what does it take to do this all around the world, right? And really make scalable, dispatchable, baseload green energy from these type of wells work? It'll require collaboration. Very diverse, multidisciplinary collaboration by a number of different parties. All of these parties right now have bits and pieces of the puzzle, but nobody is stepping up to be the integrator. So academia, national labs, service companies, oil and gas operators, geothermal companies, we need to band together and work together. And somebody, of course, needs to fund this and invest in this with some visionary leadership there, right? Not just from the perspective of we're going to make a killing in profits, right? We're going to also do something great for the planet. So government, industry, private equity, philanthropy all have a role to play there. As I said, it will require integration and coordination, right? I'm just giving an example here from my friends at Baker Hughes. Baker Hughes has developed motors that will work at 300 degrees centigrade, and they can develop chimera bits at 300 degrees C, but they're not doing that right now because there's no market. And they don't have any R&D budget right now. These companies are struggling to survive. So if you want to work with them, and I certainly recommend that you do, you need to fund their R&D organization. You focus on applied R&D with a high kind of technology readiness level. There are 9 levels, and you need to be above 4. And you want to focus on a relatively short-term time horizon, so less than 10 years. But you can start today, as I said, with hot shallow loops in existing geothermal areas. What you were thinking about there is kind of a geothermal Manhattan project, a project for geothermal that kind of mimics the Manhattan project. Okay, so conclusions. I hope I've shown you that deep closed loop geothermal systems, if they can be drilled, can provide scalable, dispatchable baseload green energy around the world, irrespective of location. It's a serious alternative to EGS. It provides some non-trivial challenges, although a lot can be done right now already. And you go at it with a phased technology maturation and implementation staircase. Geothermal right now, I think, is where wind and solar were 20 years ago. And if you see the same level of investment, possibly accelerated, it could grow at the same level or even exceed it, right? It's a very exciting future, I think, that is possible for geothermal. Upcoming papers, I mentioned this to you. SV 204097 is the one that's coming out next month. So take a look at that one. For drillers, we have a bright future. We'll drill oil and gas wells. We'll continue to do this. The best thing for the planet right now is to switch over from coal to gas. I think most people realize that. It'll cut carbon emissions in half immediately. We will always drill oil and gas wells for petrochemical purposes, but we'll broaden out into geothermal well drilling. We're already drilling extraterrestrially on other planets. Yes, you can use geothermal on Mars as well. It's the delta T that is important. And then some people are seriously looking at mining asteroids. Just Google asteroid mining, and you see what several entrepreneurs are looking at mining asteroid. So a good future for drilling. With that, I thank you for your attention, and I don't know if I have any serious time to answer questions. I've already gone over time with my lecture, but I hope you found it interesting.
So thank you so much, Eric. It was very thought-provoking and informative. So the main limitation on time for questions is just how much time you have, Eric. Just, however much time you're willing to give us for the questions. I don't know if you have your chat up, if you want to read from the chat, or maybe what I can do is I can call on the people in the order that they put questions out. Are you okay with that?
Yeah, sure.
So James Michael Eros, do you want to ask your question?
Sure, thanks. This question is mainly related to your last slide around economics and relates to drilling costs. In looking at some of the recent examples that Ever Technologies has put forward in their Germany example, it looks like they are proposing that there is a pretty significant cost reduction in future drilling costs just due to things they're seeing. And as you pointed out, there's not very much data anywhere for extant closed loop systems. I'm just curious if you have an opinion on that. And maybe a follow-up question is more related to parasitic load reductions through things like using CO2 carrier fluids for a thermosiphon effect. That's something that a number of folks have proposed. There's some debate among that, among, I guess, at least a few of the operators.
Yeah,
Thank you.
so those are several questions in one, right?
Yes, fair.
Let me answer the first one first, right? And I know this really well because I was technology implementation manager for unconventional shale before I left Shell, right? When we started drilling our first shale wells. Well, let me actually give another example. Before we started drilling the first wells in a more conventional play in Wyoming, the first wells were 60-day wells, right? And then through an organic learning curve, ultimately Shell ended up drilling these wells in a week, right? So from 60 days to a week. And in shale, we've seen many of these same kind of examples, right? Where wells first took multiple weeks and then now they're hammering them out in less than a week. And that's all been drilling efficiency optimization, kind of really being rigorous about drilling faster, keeping the bit on bottom drilling, doing technical limiter redesign, so eliminating limiters, and being rigorous about eliminating flat time, right? And we need that same approach in geothermal as well. Although, as I said, we have less of a volume of wells to play with. So you can't rely on this organic learning curve. You need to sharpen the pencil a little bit more on optimization. And so that is key. And then you can see very dramatic cost reductions. So when I talk to people, I don't want to raise any undue expectations. The first wells that we're going to drill, according to my designs, are going to be expensive wells, but then there is a lot of opportunity to get the cost down. On the what we've already seen in our modeling. So your second question, right, is on kind of the fluid that you use and the thermosiphon effect. Yeah, of course, the fluid that you use has a big effect on the overall economics, and you have to strictly what we find is that we have to strictly contain actually the thermosiphon effect and the phase behavior in the well, and we actually do that with managed pressure drilling technique, or what we call managed pressure operation techniques, through automated choke control in the operating phase. So you can't run a thermosiphon kind of uncontrolled in a well like this.
Okay, Eric, I'm going to ask a question for Mario. He said his connection is noisy. So he says, how do you see the role of MPD technology in this development? Is there any necessity to improve the development of bearing assemblies? Temperature limits? Could a mud cooler be required? Yeah,
no, and I'm assuming this is Mario Teixeira.
Yeah.
And yeah, I mean, I'm a big fan of managed pressure drilling technology, and I think it could be a real game changer for geothermal wells. I'm showing kind of the technologies that I'm most excited about, which is continuous circulation, right? Circulation, even when you're making connections, that'll give you a very stable temperature profile in the well. While you're drilling, you won't go through thermal swings. Surface back pressure technology to manage drilling margin and losses, and then potentially a pressurized or floating mudcap drilling if you deal with really severe loss circulation. And then of course also managed pressure technology in the operating phase. So yeah, I see a big future for this, and we will have to kind of develop the systems for this as well. Luckily, the surface systems, right, the temperatures are a little bit more amenable, as you saw, right, when we brought the fluid back to surface for this well that had a downhole temperature of 225 degrees centigrade. The surface temperature was 150. So you have a little bit more leeway there, a little bit more freedom, a little less stringent on the temperature requirements, for instance.
Okay, Eric, I have quite a few in the queue here, but hopefully we'll be able to get at least to the next three. So James Lovekin, and then Diana Allard, and then Jeff Hildebrand. So James, do you want to ask your question?
Certainly. Thanks for the opportunity. And I believe the professor has already addressed it partially in terms of managing the pressures of operation. But can you elaborate on why it makes sense not to allow, in the operation of a closed loop system, having the fluid flash to steam?
Yeah, I mean, I'm just very concerned about the depressurization that would happen in the well itself, especially if you go to an open hole completion, right? What we don't want is that the wellbore destabilizes. So that is, I think, why we will have to properly manage the pressures within the well, and especially kind of cycling of pressures and temperatures.
Thank you.
Diana?
Hello. Well, my question is a little bit more about like the data analysis and machine learning and this type of techniques used where there are some workflows that are going to get like the current data that is existing for oil and well and oil and gas that it has been used in the wells and production and exploration, and kind of reinterpreted or reuse that data for geothermal. So when do you see that this is a like a stretch, or when it's useful? What is the criteria for as people they're working with that type of data?
I don't know if I understand the question properly. Can you rephrase it?
Yeah, I think that probably it's about more about getting the data that has been used historically in oil and gas. I don't know, like production data from one well, for example.
Sure.
And use that data specifically for reinterpreted or try to see in terms of geothermal, parameters, or how it will behave if that well will be like a geothermal well, for example. Like in these type of things, like it's a good approach, what we should have in mind when we are using that data that historically has been for oil and gas.
So reusing kind of oil and gas data for geothermal purposes, right?
Yeah.
Yeah, and of course that's going to be very relevant for situations where you can do oil and gas production and geothermal well production side by side, right? There are many places in the world where that is possible, and where well information from oil and gas is going to be extremely relevant. Knowledge is power. Knowledge is money, right? Data is money. Ignore it at your peril, right? It's amazing what we've learned, for instance, from shale wells, from analyzing data. And so you really want to maximize it. It's just such low-hanging fruit, I would say. And I have several examples of member companies of Rapid that have done extremely well by just being very diligent about analyzing their data and then acting accordingly. And I don't see that in any way being different for geothermal.
Okay, Eric. So Jeff Hildebrand. So welcome. You all know that Jeff is a great partner of the department, our namesake. But so Eric, he's got a couple questions. Let's see if I can help him unmute here. Let's see. Sorry. Oh, did he drop off?
I still see his name.
I don't see him. I don't see his name on the list anymore. Oh, there he is. Let me click on unmute. Okay, so you have to respond to my request for unmute. Oh, he dropped off. Okay, so we will come back to Jeff. Let's see. Andrew, oh, who's here? Yeah, Andrew Van Horn. Or I'll read the question here. All the DOE R&D is directed towards EGS. What plans and projects do you think will convince DOE to go to closed loop R&D funding?
Well, I mean, we've already talked to DOE and ARPA-E. And through presentations like this and writing papers and educating them, I hope they will start to take more notice, and I think they have, to start considering this as an alternative.
Hello,
Oh,
John.
yeah, there we go.
How about now?
Sorry, Jeff.
No, I'm here.
Maybe your audio is bad. Maybe type your question to chat, Jeff.
Oh, can you hear him?
Hi, Eric. Can you hear
Yeah.
me?
We can hear you. Yep.
We can hear you.
Can you hear me now?
Yes.
Okay, sorry. All right. Hey, Eric. Thanks. Great presentation. A couple of things. One, can I get a copy of the presentation? That'd be great if I could. I just want to go through it kind of in more detail.
Absolutely. Well, I'll send it to you, and this is also going to be published on YouTube, so the whole thing is actually going to be available.
Got it. Okay, good. And then secondly, mine are a bit more commercial in nature, and that is, if from your experience, I mean, who is best in class at this right now, either US, Canadian, or worldwide? Are they actually doing these? I mean, has there been a successful implementation of the closed loop system? And then thirdly, is anyone trying this on shallower rocks, where you've got a geothermal gradient that may not be 200 C, but maybe it's 150, and while you may not produce 50 megawatts, you may produce 25. So two questions. One, who's best in class, and are there a lot of companies doing this? And secondly, which companies in America are doing this on a shallower basis? Okay.
So let me address that. So yes, there is quite a bit of activity going on in the US, right? Of course, in Iceland, this is their bread and butter. There's a lot of experience there. And then the Europeans have done quite a bit of this as well. But mostly what they've worked on almost exclusively is kind of EGS, right? Very few have started doing closed loop. The only closed loop that I know of right now is being done by Ever in Canada. But that doesn't mean that you can step. I mean, what I've shown you is kind of conventional drilling technology, right? Conventional operators can drill closed loop wells. There's no magic to it in this. The idea that I've given you in this presentation is thinking about kind of existing geothermal wells, right? Or geothermal areas where you have higher gradients, and drilling shallower hot loops there, and proving up both the drilling technology as well as some of the modeling and the economics. It's kind of a low entry to kind of de-risk going into deeper areas and spending more money. And I think that can be arranged. That can be arranged right now.
Good. I mean, for me, that's, to go out and spend, let's see, one of your numbers was 80 million for 50 megawatts. I mean, that's a tough putt, as they say right now. But yeah, no, I think it's very exciting. And, I've said, while you disparaged you didn't, not that strongly, but the oil and gas industry thinking they can be the geothermal gurus, as you aptly pointed out, there are many resources and skill sets and abilities that the oil and gas industry can bring to bear in the geothermal industry. I've always had a unique interest in it, just prior to the whole energy transition discussion. So to me, it's very exciting, and uses the skill set that we've developed here at Hillcorp and a lot of other companies to potentially, enter into the energy transition world. So look, more to follow. I'd love to come up to Austin and meet you personally. I've heard great things about you, and maybe bring a couple of guys up and sit down and really do a deep dive with you if you've got some time at some point in time over the next couple of months.
Yeah, sounds good. Sounds good.
Okay, great. Thank you.
So Eric, you have time for one more question?
Yeah, absolutely.
Rob Peters, do you want to unmute and ask your question?
Yeah, sure. Hi, goedemiddag, Eric from the Netherlands. Very nice presentation. Thanks very much. Yeah, one thing you often hear about closed loop systems is the temperature drop that's expected from the formation, given that most rocks have a fairly low heat conductivity. I noticed in your simulation that it seems to reach an equilibrium. Is that right, after 1200 minutes?
Yeah, it kind of reaches an equilibrium. And yeah, I mean, you see a significant temperature drop, right? That's why we need to go to higher temperature environments as well.
Yeah.
That's why we need to be above. I mean, it becomes rapidly kind of uneconomical if you go to lower temperatures, right? Yeah, I mean, it's still a semi-infinite reservoir that you have. So you'll reach a steady state, but you could maintain that steady state for a very, very long time, as long as you have enough heat flow, of course, from the far field.
Yeah, I was just interested in that respect. What was your heat conductivity that you used in that model?
Oh, I'd have to go back to it. It's actually in we have it in the papers, right? And we've modeled it on the granite, I think. Yeah.
Okay. I'd love to read your paper. So that's going to be published soon?
Yeah, it's going to be published in a month, right, at the SPIDC drilling conference, which was supposed to happen in Stavanger. I was looking forward to the trip to Norway.
Yeah.
But now it's going to be fully virtual. But yeah, so the first week of March, in the kind of alternative energy section of the conference, the paper will be published.
Okay, that's great. Thanks very much.
So just one quick thing before everybody leaves. I just posted to the chat again the link to the Hildebrand Department's YouTube channel, where if you go under the Spring 2021 Graduate Seminar Series, you will find Eric's talk there in the next day or two. I'm sure if you communicate with Eric, he can also give you information if you'd like. I see there's another question, Steve Longfield from Ever.
Yeah, hi Eric. Excellent talk. Thank you very much.
Thanks, Steve.
Yeah, just on that, following up on Rob Peters' question there, what's that radial cooling distance into the formation from the simulations? Is that exactly at the wellbore?
Well, what I'm displaying in that graph is the temperature at the wellbore, right? But we actually are modeling it inside the formation as well, all right? So in the modeling approach, we actually look at the formation as well, right? So you have elements there that you model inside the formation until you get to kind of far field conditions.
Okay.
And again, I don't know exactly. Usually, I mean, if you look at thermal effects, right, they usually die out several wellbore diameters into the formation. What the exact number is, I would have to check.
Okay, thanks very much for the talk.
Yeah, my pleasure.
Well, thank you again, Eric. Had a great turnout today, a lot of interest, a lot of questions. I think we can probably wrap up the formal session. I don't know if you can hang around any, Eric, afterwards to talk more informally on the session, but
Sure.
But we can leave it open if you want to talk to anybody that's here. But I think it looks like we have most of our set questions done. So thanks again, and thank you everyone for attending. We appreciate your interest, and we have this seminar pretty much every Monday, not geothermal every Monday, but we have a seminar every Monday, and you're welcome to come back.